Welcome to the session on integration, modelling with differential equations. The objectives for this session are to model real-life situations with differential equations. We can use differential equations to model real-life situations. Let's take a look at this example. The rate of increase of a population P of squirrels at time t in years is given by dp dt equals k times p, where k is greater than 0. Initially, the population was of size 200. Take a look at some of these questions related to the example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at part A first. We will find a model for P in the form P equals ae to the power kt. Here's our differential equation, dp dt equals kp. Let's integrate this expression. We've used this formula. So integrating the right-hand side gives us kt plus c, where c is our constant of integration. And integrating 1 over p with respect to p gives us ln p. We now raise both sides to the power e. And of course, e to the power ln p gives us p. So we have p equals e to the power kt plus c. Which can also be written as e to the power c times e to the power kt. Now when t equals 0, we know that p is equal to 200, so we can now find the value of c. Plugging p equals 200 into our equation and plugging t equals 0 into our equation gives us that 200 equals e to the power c times e to the power 0. So we have 200 equals e to the power c. And therefore, this implies that p equals 200 times e to the power kt. Now let's take a look at part B. Given that k equals 3, find to the nearest hundred the size of the population at time t equals 2. Now from part A, we have this equation for p. Now given that k equals 3 and t equals 2, we have that p equals 200 times e to the power 3 times 2. And plugging this into our calculator gives us the value of p as shown. Now since we're required to find population to the nearest hundred, we know that population is therefore equal to 80,700. Now let's have a go at part C. Given that k equals 3, find the time taken for the population to reach 4,000. So we have k equals 3 and p equals 4,000. From part A, we also have that p equals 200 times e to the power kt. And therefore, putting both of these parts together, we have 4,000 equals 200 times e to the power 3, which is the value of k, times t. Rearranging this, or dividing through by 200, gives us e to the power 3t equals 4000 divided by 200. And then taking ln of both sides gives us that 3t equals ln of 4000 over 200, giving us this expression for t, which is equal to 0.999. And this is, of course, approximately equal to 1 year. And now for part D. We are required to find a limitation of the model. One limitation of this model is that the population cannot increase in size in this manner forever, due to the limitations of space, food, and so on. Now let's take a look at another example. A mug of coffee with temperature T degrees Celsius is made and left to cool in a room with a temperature of 25 degrees Celsius. The rate at which this coffee cools is proportional to the difference in temperature between the coffee and the room. Take a look at these questions related to this example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. We're required to find the differential equation which describes this process. This is given by dt equals minus k times t minus 25. Let's now link all the parts of this equation back to the question so that we can see where all the parts come from. dt is the rate at which the coffee cools. The difference in temperature between the coffee and the room is given by T minus 25. The constant K has to be positive in this equation, or the coffee would be warming. Notice that the coffee is of course cooling, and it's also proportional to the difference in temperature between the coffee and the room. Now let's take a look at part B. Initially, the coffee has a temperature of 85 degrees Celsius. After 10 minutes, the coffee has temperature 55 degrees Celsius. We are required to find the temperature of the coffee after 12 minutes to 1 decimal place. Now from part A, we have this expression for dt, which is of course minus k times t minus 25. This implies, if we integrate, that integral of 1 over t minus 25 dt equals integral minus k dt. Here we've used this formula. So integrating gives us ln of t minus 25 on the left-hand side and minus kt plus c on the right-hand side, where c is the constant of integration. Now we also know that when t equals 0, capital T equals 85. And so plugging in capital T and little t into the equation gives us ln of 85 minus 25 equals 0 plus c. And this implies that c equals ln of 60. Therefore, we've found our constant c, and we can plug this back into our equation to give us ln of t minus 25 equals minus kt plus ln of 60. We also know that after 10 minutes, the coffee has temperature 55 degrees Celsius. And so substituting these values into the equation, gives us ln of 55 minus 25 equals minus k times 10 plus ln of 60. And rearranging this, we can start to find the value of k. So we have 10k equals ln of 60 over 30. And therefore k equals 1 over 10 times ln of 2. Substituting this back into the main equation, as shown, gives us this expression. And rearranging this, and also using the formula x ln a equals ln of a to the power x, gives us this expression. And using ln of ab equals ln a plus ln b, gives us this expression. And therefore clearly t minus 25 equals 2 to the power minus t over 10 times 60. And now we can plug in t equals 12, since we're required to find the temperature of the coffee after 12 minutes. Giving us that the temperature is equal to 51.1 degrees C. This brings us to the end of this session. If you have understood its contents, you should be able to solve simple differential equations. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.